Hello everybody, and welcome to video series on linear regression. Part 1 of this video series is mostly introductory. In this part we will explain what linear regression is and how it stands compared to other similar methods and models, and what role it plays in the machine learning in general. Linear regression is a prediction model. The task it solves is to predict some kind of output value y if you know a series of input values x1, x2, etc. xn, or in other words, if you have a multi-dimensional vector x. The practical example of this prediction would be, let's suppose we keep some network of shops which are selling soft drinks. And we want to predict our output value, which is amount of sales. This would be our y, our output value. And our three input values could be the weather, the population, and the competition. Weather obviously affects amount of sales for soft drinks, because the warmer the weather, the more frequently people would be buying soft drinks. Population obviously also have some impact on this. I mean population in the area where the shop is located. And competition means how many other shops are there in the same area which are also selling soft drinks. It will obviously have some kind of negative impact on our amount of sales. So knowing all three values, we want to predict our output value y, and the practical use of this task could be, suppose we want to open a new shop, so we have some data collected for our existing shops, and we want to open new shop in some kind of new location, and we want to know what amount of sales would we expect in this new shop. And all these three input values are available. Weather data, weather statistics could be obtained from some weather agencies. Population is obviously also known from some statistical sources, and competition, how many other shops are in the area, is also known because this is open business data. Linear regression is part of machine learning, which in turn is part of data science. Therefore, machine learning is a branch of science, but I would say it's very unusual science. It's very different from classic science. In classic science, for example, in physics, in chemistry, in biology, in all classic sciences, we first learn the process we are dealing with. And we try to describe this process with some kind of model m of x, where m could be as a set of equations of independent variable x, or it could be a set of algorithm or any other means of expressions or expression of this model. Now, having this model, we can analytically produce our output value y, which has been calculated by this model, or we will normally write some kind of software which will be implementing the model and calculating our output value. In machine learning, the approach to this problem is almost other way around in terms of sequence of actions. In machine learning, we first have set of data. We already have some kind of output data, and this data could be obtained from real life, from some kind of experiments, or gathered from existing statistics. And then, based on this data, we want that our machine, meaning our computer, learn this data and build some model which will describe this data, and machine is supposed to build this model itself. So we are not building model, machine is building this model for us. And once we have this model which was built by machine, we can start predicting our output value y, knowing our input values. And please notice we say predict output value y, we don't say calculate it, and this reflects the fact that this prediction is not expected to be precise. Within machine learning, we cannot produce precise results. We cannot actually say for sure what our output value would be, but we can try to predict it. There is one interesting point about classic science, whether their results are precise. It's actually a big question whether they are precise or not. They often pretend to produce precise results, but actually their results are also approximate. They are also not precise because no mathematical model in the world can describe any practical physical process precisely. So they're also making some kind of assumptions. But in some cases, analytical model will produce more precise results than the model which was worked out within machine learning. So in machine learning, it is a machine who learns, not the human person. And there is very interesting question arising from this fact. So does it mean that if we have machine learning, we no longer need to know about our process? The machine will do everything for us and we can just relax and wait for results to come? Unfortunately, absolutely no. The same as it was in classic science, in machine learning, it's also important to have as much knowledge about the process as possible. And the more knowledge you have, the better machine learning model you will pick up, and the better you will understand how to obtain results and how to interpret them. Linear regression, as almost everything in machine learning, has strong mathematical background, which is important for understanding of how it works. So let's briefly explore the math background of linear regression. Currently, you see some visualization on the screen of a very simple case. And this case is where you have only one input variable x and obviously one output variable y. The green dots shown on this picture are depicting your experimental data. These are data which you have so far, and each dot represents pair of x and y, so it will tell you that at some point you had this input value x and it produces that output value y. And by knowing this, you want to make prediction for your future x values, for some another x value which you do not have experimental data for, but which you want to find out what possible value y would be. In linear regression, your prediction function would be linear. It means that you will be trying to build some line like this. And this line is going more or less describe your experimental data. It's not going to precisely match your data, but it's going to show some tendency, and it is assumed that your future data will be also grouped around this line. By the way, doing these graphical visualizations is very important way to decide whether linear regression is good for you or not. For example, let me briefly remove this line and get back to our original raw data, and let's have a look at how these green dots are shaped in this picture. As you can see, they are somewhat grouped around some line, around some straight line, and this is indications that linear regression probably would be a good fit for this data. Or otherwise, if they were not grouped around any line, if they were spread differently, or if they were in totally random order, you can make conclusions that linear regression is not a good candidate for building a prediction model for this kind of data. Unfortunately, these graphic visualizations are only possible in very simple cases. For example, the two-dimensional case we are currently looking at, or maybe in three-dimensional case where you have two input variables and one output variable. They will not be useful if you have many variables. But don't worry, there are methods available where you can assess whether linear regression would be good even if you have many variables, and we will review these methods later. So once again, you want to build a line which will connect these dots or somehow represent them. And analytically, this line could be expressed with expression kx plus b, which is known in algebra as linear expression. So any expression which only has additions and multiplication by some constant is known as linear expression. And why it's called linear, it's very clear from this picture because it describes straight line. So our task in case if we have only one input variable is to pick up this coefficient k and value b, and after we pick them up based on our input data, we can then use them on our data in future. We can have some other x values which we will fit into this formula, and this formula is going to produce our output value y for us. So far the approach looks fairly simple, but is it really that simple? The interesting question here is how do we build this line? We already have some blue line, but would it not be, for example, possible to use this yellow line? As you can see, it also somehow represents these values, or maybe this green line. How do we decide which line would be the best? And remember, we cannot just look at the picture because we are developing machine learning, so it's machine who should decide, not we, and machine is obviously not able to look at this picture. So it needs to have some kind of analytical method, some kind of calculation method to find out what line would be the best. And this case illustrates that despite of the fact that linear regression is very simple and basic prediction model, it's not really 100% simple and basic. Even with linear regression, you already have some kind of challenges and problems. So let's have a look at this problem in more details. Suppose we have only three values, only three green dots, and we want to build our blue line. How would we build it? Obviously, we want our green dots be as close as possible to this line. So we want to minimize distance from each dot to this line because this distance represents so-called error. The error means that we are not hitting directly these dots. Ideally, we want to build line which will connect all three dots, but it's not possible as we have only one straight line. So these three values, we will mark them as L1, L2, and L3 are our errors, and we want these errors to be minimal. But it's easy to say, but not very easy to implement, because if, for example, we make L1 equal to 0, in this case, L3 will be very big. If, as opposed to this, we make L3 equal to 0, L1 would be big, and L2 probably will be big in both cases. So what approach will we use to find some compromise with this error? Actually, we need to have some kind of cost function, and this would be some kind of expression which depends on all our errors, and this expression we are going to minimize. The most popular choice of cost function for linear regression is so-called mean square error function. Mean square error means that we are finding squares of all our errors, we summarizing them, and we divide them by n. This will make them to be mean, but for the purpose of finding minimum, we may not even divide them by n. I'm just showing one of the typical form for this expression. Or in other words, if you look at the right part of expression, we will need to find squares of differences between our y hat value, this is our predicted value, and our original y value. Then we will need to summarize this, and our goal is to minimize all this expression. There could be also approaches based on different cost functions, but as I already said before, this cost function, mean square error, is most popular in linear regression. One of the reasons which is making it very convenient is because, as you can see, This function is built that way so it would penalize big errors. So if you have pretty big error and you find square of this error, you will have really very big value. If, as opposed to this, you have very small error, only some very tiny deviation from the line, in this case, square also will be a very small value, and this wouldn't be very noticeable in this formula. Now, how to minimize the expression which you currently see is a very big story on its own. There are numerous methods available, and fortunately, linear regression has so-called analytical solution, so you can minimize it exactly. You can actually use some exact formula for minimizing this. And there are many calculation methods which will find some approximate solution for this. All these methods are somewhat beyond of the scope of this video series. They are all interesting, but it will take very long time to review them. And you are very encouraged to look at math background of linear regression in some books and materials on internet. There is plenty of them available. Within these videos, we will be more concentrating on some kind of practical examples of using linear regression within Python. And the next case which we can still successfully visualize is when we have two input variables x1 and x2 and still output variable y. In this case, our dots will be presented in three-dimensional space as shown on this picture. Our task will be to pick up the flat which will fit these dots, and this flat equation is the same linear equation as we saw before, but now it has another component, now it depends on x2 as well, not only on x1. So our task will be to pick up flat which would be the best in terms of minimizing cost function. We can still use the same cost function based on mean square error, and we will have to pick up coefficients k1 and k2 and value b. Value b is actually known as intercept. We need to pick up all the three constant values which will provide us the best flat, the flat where these mean square errors will be minimal. In general, if we have n input variables x1, x2, etc., xn, we will need to build linear function of n variables. So our task will be to minimize our cost function. As we already know, the most popular function is mean square errors. However, some other functions may exist as well. We will have to minimize this function and pick up the best set of coefficients k1, k2, kn and intercept b. And unfortunately, as you can probably understand, that was the last case where we can provide effective visual representation. If we have 4 variables, 5 variables, or more variables, we cannot really visualize them, or at least we cannot visualize them easily and effectively. In this case, we will need to resort to some analytical methods, which will tell us whether we are doing good or not. So whether we are really finding some linear regression solution which will fit our experimental data, or we really need to turn our head to some different prediction model, I mean different from linear. Linear regression is based on numerous assumptions. The first assumption and the most fundamental one is already known to you. This is assumption of linearity. This is assumption that dependency of the kind of dependency your output variable has from input variable is linear. But this is not the only assumptions. Another assumption is actually that you selected correct input variables, and this is also pretty difficult problem. So if you have certain input variables, for example, you have a, b, and d, or b, d, and g, or other input variables, which exact input variables you need to put into your model? You can actually make error from both sides. You can have too many input variables and too few. Too many means that you may include some input variables which are totally irrelevant for your task. So you can put some variables which do not define your output value at all. However, if you formally apply them, it will very much complicate the model, and it will potentially lead to some errors. Or you can use too few, means that you may not include input variable which is very important for you. And the variables you are using may be not as important as that another variable. Let's remember our previous example with soft drinks shop, where we made assumption in that example that our amount of sales, our success of business depends on 3 input variables, which was the weather, the population in the area, and the competition. It's quite possible that it much more depends on something else. For example, it may depend on cultural tradition of people who live there. Some people simply love soft drinks and drink them all the time, but within some cultures there could be people who do not drink soft drinks at all, regardless of what the weather is or what population is in this area. So we need to be sure that we are using correct variables. You may think that this advice about variables is pretty simple and basic. However, it's only simple within a lecture, within some kind of study. Within real life, the problem is that you do not know exactly what your input variables are. You could be given some variables, some kind of information, and this information is not specifically prepared for machine learning. This is just some information from some statistical sources. So it's your task to decide what input variables to include. And yet another important fact about input variables, which is sometimes been overlooked, and this is the fact that your input variables should be all independent, meaning they shouldn't depend on each other or on the set of other variables. Let's consider such example. You are predicting value of the house for the family, how big this house should be. And as input variables, as sum of input variables, you use number of children in the family, and you have input variable which is number of adult children, and you also have input variable which is number of non-adult children, and another variable which is total number of children, how many children this family has in total. Obviously, this number is just the sum of previous numbers. Total number of children is simply sum of adult and not adult children. However, if you formally put into a model, you will obscure some calculation algorithm because it will try to treat it independently, and it will try to pick up some separate coefficient for this variable. And once again, you may argue that this is very obvious fact, that obviously if you have some kind of sum of previous values, you should not include it. Why it's not so obvious? Again, by the same reason as I already explained it before, your real data which are given in real life may contain it, because people who were giving you this data, they did not specifically tune this data for machine learning. They just gave you all data which were available. Some customer can simply give you such data, and it is your task to separate unnecessary data from those which are really required. And another assumption we are making in prediction model is that we think that if our system behaved a certain way in the past, it will behave the same way in the future. Sometimes this assumption could be correct, sometimes it's not correct. Let's think, for example, that we are modeling some kind of physical process or some kind of technical problem. In this case, it probably always behaves the same way, and we can make this assumption. But as opposed to this, we are trying to build model of some kind of economy-related problem, and we have data, some kind of economical statistical data for the last 10 years. It probably would be a little bit naive to assume that our economy will work the same way in the future 10 years, because it's always changing. It's not really working in different period of times under the same rules. So in any prediction, you need to make sure that you are dealing with model which really behaves the same or almost the same way in the future as it was in the past, or at least follow the same rules. And please note, while assumption number 1 is mostly relevant to linear regression, assumptions number 2 and 3 are pretty common and they're actually applicable to any machine learning model. Because in any machine learning model, it is important to have a correct choice of input variables, and any machine learning model or method relies on assumption that the system will behave in future the same way as it was in the past. And this last problem is probably the most difficult and fundamental one. So, knowing how many assumptions we need to make, and if these assumptions are not true, then our model is not going to work, it's very good time to ask why at all we need to study linear regression. So is it really useful? Would we really get any kind of practical sense of this? And as you probably know, it's been well-established tradition of many presenters to declare what will you achieve at the end of certain study. So they will normally say that at the end of the study you will know how to do this or that, or you will be able to successfully perform on certain project. So following this tradition, I will tell you very honestly that it is very unlikely that at the end of this study you will be able to solve any practical complex task. And this is not because there is something wrong in linear regression, it's just because it's too simple. It's just because it's insufficient for any practical complex task, because most practical tasks are not linear. However, studying linear regression is still very important. First of all, linear regression is most well-known prediction model, is most studied prediction model. The solution in linear regression always exists, and even it can be found analytically, although it's maybe not necessarily the good solution in all cases, but at least you know it exists. As opposed to this in some other regressions or in some other prediction model, you cannot be absolutely sure that you can find even one solution. There is a so-called problem of convergence. If you're using some iterational calculation algorithm, it could be jumping around and never coming to any solution. With linear regression, at least this is not a problem. At least you can find some solution. Maybe not very good, but at least you will find at least some solution, and you can understand this fact from previous visualization in our two-dimensional space and three-dimensional space. You can understand that no matter what your dots are, you can always draw some line. Maybe it will be bad line, but some line always possible, or you can always draw some flat in three-dimensional space. The second very important fact that linear regression is actually part of the learning curve to other prediction models. So once you know linear regression, it will be way easier to learn more complex models. And if you don't know linear regression, it probably would be very difficult to understand more complex models. And this approach is normally used in all studies. Obviously, you cannot study some complex subject before you studied more simple, more straightforward subjects. So linear regression is your path to know all other prediction models and to machine learning in general. And finally, some real-life processes are really linear, or at least they could be presented this way. I already mentioned previously that in practical life you will not find linear processes. However, what I meant by this, I meant that you would not find ideal linear processes, but sometimes you will find some kind of semi-linear processes, some processes which are close to linear. I can give, as a practical example, I can give well-known Ohm's law in electricity, and this law is actually linear. It declares that your voltage and electric current are proportional to each other, and this is assuming that your resistance is a constant, it's always the same. So how precise this law is, well, is also a big question, because in real life probably resistance wouldn't be exactly constant value, it may be changing in your electric circuit. However, for practical purposes, it's considered to be useful. So at least this linear model gives some particular practical results. And finally, there is a case where the process itself is not linear. However, you can use linear regression successfully. And this is the case where you can perform linearization. Linearization is a very popular technique in different branches of math, especially in algebra and in calculus. Linearization is where you have nonlinear function, but you can replace it with a series of linear functions. For example, let's have a look at this picture and see what kind of data we have. The data shown on this picture are obviously not linear. However, does it not suggest that we can build 3 lines to connect all this data? For example, we can put this line, and that line. And as you can see, within every line, the process looks as pretty nice and linear. So if we identify 3 ranges for our input variable x, something like this, and apply our linearization separately to each of these ranges, we can build 3 linear regression models. Model for AB, for BC, and for CD ranges. Now you may ask one question. Would this model, model which consists of these 3 regression models, would this cover anything which is beyond of our identified ranges? For example, would it work for x values which are less than a, or for values which are more than d? And the answer to this, probably not. Probably it would not work there at all. But the interesting point is that we may don't care about this. And this is because in many practical tasks, ranges of your variables are very well defined and they are very narrow. And you are not really interested in anything which goes beyond of these ranges. For example, if one of your input variables is the height of a human person, then obviously this height is within well-defined limits. First of all, it couldn't be less than 0 by obvious reason. And it could not be more than something like probably 8 feet. Well, I am actually not sure how tall is the tallest person on the earth, but I think that probably 8 feet will be the maximum. So your data range is always between just 8 and 0, and you don't need to cover in your model anything beyond of this range. And if, for example, the input variable was body temperature for a human person, for a live human person, this range is even better defined. It is a very small range. The temperature is always within a certain value. It could be just up or down a few degrees, but never more than that. So linearization within certain well-defined ranges could be a very useful technique, and unlike some previous assumptions which we were making, this linearization is pretty practical approach. It could be used in real life. It's not only in academic studies. And by the way, I just thought that our previous example with shop selling soft drinks perfectly fitting into this linearization schema. Especially I'm talking about one of our input parameters, which was temperature, which was what kind of weather we have, whether it's warm or not. As you may see, this temperature will only have any influence within warm or hot temperatures. So when it's warm, people buy in more. When it's even more warm, they buy even more. But it would not be really that useful within cold temperatures. If the weather is cold, then some people will not buy soft drinks at all, and some people will buy them just because it's their tradition, maybe part of their diet, but the temperature doesn't affect them. So number of sales would not really be different when it's cold, when it's very cold, when it's very, very cold, when it's freezing, it will be always the same. So within certain data range, the coefficient of our linear function for this parameter for temperature will be 0. And only a certain range, and this range will refer to warm and hot temperatures, it will be some kind of non-zero coefficient. And once again, after this range, we simply don't care because we don't want to cover temperatures which never happen in certain area at all. Linearization approach is pretty useful, but it has its limits. First of all, it's limited for pretty small tasks, and by small I mean that you have only very few input variables. On this picture you only have one input variable, and this is why it was so nice and easy to identify these linear sections. If you have two variables, you still can do this if you have three-dimensional visualization, but having more than two variables mean that you wouldn't be able to visualize it, and find these linear ranges analytically is pretty difficult. There is one case when you can use linearization even if you have many variables, and this is the case if you have some preliminary business knowledge about your process, so you know actually some sections where you think the process could behave differently, and within this section could be linear, but each section could have different linear coefficients. And I already told you before that it's very important to have some knowledge about the process, even though you're doing machine learning, not classic science, but it's still very beneficial to know something. And this is actually the case here. Let's consider some practical example. Let's think that we're now trying to predict income or revenue for supplier of our soft drinks. And one of our input variables is the size of the order which customer are placing with this supplier. And from the knowledge on this industry which you may have, you may know, I don't know this industry, I will give some kind of data which I made up, but you may know that everything which is, every order which is between 0 and 100 bottle is charged at retail price. And everything which is between 100 and 300 is small wholesale price, and everything which is above 300 is just regular wholesale price. So these three prices are different, and you know how they are defined. You know within which range which price would apply. So if you have this knowledge, you can go ahead and build 3 linear regression models. Each would be covering this data range between 0 and 100, between 100 and 300, and more than 300. So this is how you can use your business knowledge to build proper prediction model. And finally, just to finalize this linearization discussion, I wanted to say that I previously, you probably remember, said that linear regression itself is not very useful in practical examples. And what I meant by that was that it's not very useful alone, when it's only used alone in its pure form. But when it's used as a component of a bigger model, for example, when it's used with combination as combination with other prediction model, or where more than one linear regression model is used, it could be useful in practical example as well. Of course, not every process is subject to linearization. You may have process which you could not linearize even approximately. For example, if your function is something like sinus function, which is going up and down all the time, you wouldn't be able to apply this. But there are many practical processes which could be linearized if you know data ranges where they could be more or less stable, so you could apply this knowledge. This is the end of part 1 of video series on linear regression. In this part, we learned what linear regression is, what is the math background of linear regression, and what challenges exist in both linear regression and in machine learning in general. And you are now invited to watch next parts. In these parts we will show how to do linear regression in Python. Thank you for watching.